That satisfying click of a bolt torquing down a spec, you hear it 1,000 times during a race weekend. Nobody thinks twice about it. Nobody looks twice at it. But in 1993, one bolt at Daytona International Speedway nearly blew the lid off the most sophisticated cheating operation NASCAR had ever seen, because this bolt was hollow, and through its center ran a secret passageway that funneled air around the one device NASCAR said was absolutely untouchable, the restrictor plate. This is legacy motoring, and I spend way too much time thinking about the hidden engineering war between NASCAR teams and their inspectors. If you're someone who loves the stories behind the rule-bending genius that shaped stock car racing, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Now, to understand why a hollow bolt mattered, why grown men with engineering degrees would risk their careers over a quarter-inch channel drilled through a piece of steel, you have to go back to the moment that changed everything. May 3rd, 1987, Talladega Superspeedway. Bobby Allison is running in the lead pack, and his Buick is traveling at over 210 miles per hour. That is not an exaggeration, that is the documented speed. On lap 21, his engine lets go. Debris shreds his right rear tire. The car snaps sideways at a velocity that most commercial aircraft don't reach during takeoff. What happens next nearly ended NASCAR as we know it. The car goes airborne, backward. It sails into the catch fence along the front straightaway and tears through nearly 100 feet of steel, cable, and chain link fencing. Pieces of the car shower into the grandstands. 4 spectators are injured. The catch fence, the last line of defense between a 3,400-pound stock car and thousands of fans sitting in aluminum bleachers, almost failed completely. Standing on the flag stand directly in the path of the wreckage was Harold Kinder, the flagman. He watched this car hurtling toward him, and he knelt down, held out his yellow flag, and did not move. The car landed just short of him. He didn't flinch. That same weekend, Bill Elliott had qualified at 212.809 miles per hour. As of right now, decades later, that remains the fastest official lap ever recorded in NASCAR history. Drivers were reporting that in Turn 3 at Talladega, their rear tires were lifting off the pavement. The cars were approaching the aerodynamic threshold where they would simply stop being ground vehicles. They were becoming unintentional aircraft, and the fencing designed to catch them was proving inadequate for the forces involved. Something had to change. For the remainder of 1987, NASCAR experimented with smaller carburetors at superspeedways. They mandated Holley 390 units instead of the standard 830 CFM carburetors. The teams hated them. The smaller carbs altered throttle response in unpredictable ways, made the engines feel sloppy coming off corners. It was the temporary fix, and everyone in the garage knew it. By 1988, NASCAR introduced what they considered the real solution, the restrictor plate. The drivers had other names for it. Most of those names would get this video demonetized. Here's the thing about the restrictor plate. The concept is almost insultingly simple. Take a flat piece of aluminum, roughly a quarter-inch thick, drill 4 holes through it, bolt it between the carburetor and the intake manifold. Those 4 holes become the only pathway for every molecule of air trying to reach the engine's combustion chambers. Less air means less fuel can be burned. Less combustion means less power. A typical Winston Cup engine produced somewhere between 750 and 800 horsepower without restrictions. Put a plate on it and you were down to roughly 450. Nearly half the engine's capability gone, eliminated by a slab of metal you could hold in one hand. The hole diameters varied over the years depending on what NASCAR wanted the speeds to be. Generally, they ranged between 7/8 of an inch and 1 inch. NASCAR controlled the plates. They handed them out at the track, they serialized them, they sealed them after installation. This was the one area where the sanctioning body drew an absolute line in the sand. Do not modify this component. Do not touch it. Do not even think about it. So naturally, every crew chief in the garage immediately started thinking about it. And here is what most people don't realize about why the restrictor plate created such an irresistible target. These were purpose-built race engines designed from the ground up to breathe. Every aspect of their construction, the portwork and the cylinder heads, the cam profiles, the header dimensions, the intake runner lengths, All of it was optimized to move the maximum possible volume of air through the engine as efficiently as possible. The restrictor plate was like putting a cork in the throat of an Olympic sprinter and telling him to run the 100 meters. The engine was begging for air it could not get. The teams did not need to add horsepower, they needed to recover horsepower that was being stolen from them. And at superspeedways where 43 cars ran in drafting packs separated by inches at 190 miles per hour, even a small advantage in airflow translated directly into speed on the track. Now, you might be thinking that 10 or 15 extra horsepower does not sound like much. In unrestricted racing, you would be right. A 15 horsepower advantage at a short track might gain you 1/10 of a second per lap. Nice, but not decisive. The slower car can make it up with better driving, better chassis setup, smarter pit strategy. But restrictor plate racing was different. Because every engine was being choked down to essentially the same output, the performance window was compressed. Everyone was operating so close to the same absolute ceiling that tiny differences became proportionally enormous. The plate was supposed to be the great equalizer. Instead, it became the ultimate prize for whoever could defeat it most cleverly. The early approaches were blunt instruments. David Pearson, one of the greatest drivers in NASCAR history, later recalled that when restrictor plates were first used in the early 1970s, his crew chief, Jake Elder, had a straightforward method. Elder would cape a counterfeit plate under the fan shroud cover before the car went through inspection. NASCAR would hand the team their official serialized plate, the crew would turn around as if they were installing it, and Elder would pocket the real one and bolt on his own version. His version had holes that were just slightly larger. A little careful knife work around the openings of a homemade plate could pick up 10 horsepower without any visible difference to a casual observer. Pearson said he would drive just fast enough to stay in contention without attracting suspicion, and they got away with it. For a while, until Elder lost his temper during a post-race inspection. An inspector wanted to check the plate, and Elder, in a moment of frustration, ripped the seal off himself. Bad move. NASCAR told him to pull the entire carburetor assembly for a full inspection. The jig was up. Then there was the legend, and I use that word deliberately because the details vary depending on who tells the story, of the restrictor plate made of cardboard and wrapped in cigarette foil. From above, looking down through the carburetor throat, it looked like aluminum. It had the right color, the right sheen. It passed visual inspection without raising an eyebrow. But the moment the engine fired and manifold vacuum built up, the pressure differential sucked the fake plate right through the intake and blew it out the exhaust. By the time the car rolled off pit road, the plate was gone, destroyed, dispersed as ash and fragments through the headers and out the tailpipe. The engine was breathing completely free, unrestricted, making every horsepower the builders had designed it to produce. Whoever conceived of that had a beautiful understanding of NASCAR's inspection procedures and the physics of airflow through an internal combustion engine. They also had extraordinary nerve. But those were the old days, the era of shade tree ingenuity and inspectors who checked things with their eyes and their hands and not much else. By the late 1980s and through the 1990s, NASCAR had gotten significantly smarter. The plates were serialized and tracked. Inspectors checked them before qualifying, after qualifying, before the race, and after the race. They began X-raying carburetors. They used dye-penetrant testing to trace airflow paths through components. The obvious cheats, the ones that relied on swapping plates or using fake materials, were effectively dead. So the engineers went microscopic, and this is where the story gets technically fascinating.
The restrictor plate is a choke point. All air flowing to the engine must pass through those 4 holes. But the plate does not exist in isolation. It sits sandwiched between 2 other components, the carburetor above it and the intake manifold below it. These 3 pieces are bolted together as an assembly, held in place with fasteners, sealed with gaskets, and anywhere 2 machine surfaces meet, anywhere a fastener passes through a bore, anywhere a gasket sits compressed between metal faces, there exists a potential pathway for air. The engineering question that consumed the smartest people in the Winston Cup garage was deceptively simple. Can you create an alternate route for air to reach the engine, one that bypasses the plate entirely, without leaving any visible external evidence? The answer, discovered by the engineers at B&R Engineering in Winston-Salem, North Carolina, was yes, and the method was breathtaking in its elegance. Look, here is how it worked. The intake manifold bolts to the cylinder heads using studs that pass through the manifold flanges. Some of these studs also pass through or near the restrictor plate mounting area, where the restrictor plate is sandwiched. Normally, these studs are solid pieces of steel. They are structural components. They hold the assembly together. They are among the most boring, unremarkable parts on the entire engine. Nobody gives them a second glance during inspection. Nobody has any reason to. But what if one of those studs was not solid? What if it had been carefully drilled out through its center, creating a hollow tube? What if the carburetor body had tiny passages machined into its casting that connected to the hollow center of that stud? And what if the intake manifold had matching passages that connected from the other end of the stud into the intake runners? Suddenly, you have built a secondary air circuit, a parallel pathway. Air enters through the machined passages in the carburetor, flows down through the hollow center of the stud, and dumps into the intake manifold on the engine side of the restrictor plate. The plate is still there, still bolted in place, still sealed, still looks absolutely perfect under visual inspection, but it is no longer the only route for air to reach the combustion chambers. The genius of this design was its near total invisibility. You cannot see the internal passages without physically cutting the components apart. The hollow stud looks identical to a solid one from the outside. Same dimensions, same threads, same torque specification. The drilled passages in the carburetor and manifold were hidden deep inside the castings, invisible to any inspection method short of X-ray or destructive testing. Even Gary Nelson, who had taken over as NASCAR's competition director and chief inspector, admitted publicly that he had spent years as a crew chief staring at carburetors and intake manifolds, trying to figure out a way around the plate. He never found this approach on his own. The discovery came almost by accident. July 1st, 1993, Daytona International Speedway, Pepsi 400 qualifying. Ken Schrader, driving the number 25 Hendrick Motorsports Chevrolet Lumina, puts down the 15th fastest qualifying time. Not spectacular, not suspicious. Schrader was having a solid season, running 7th in Winston Cup points, riding a streak of 4 consecutive top 5 finishes. He was a legitimate championship contender, which made what happened next all the more consequential. After qualifying, NASCAR inspectors began their standard post-qualifying technical inspection. Nelson's crew was pulling the carburetor off Schrader's engine, following routine procedure, when one of the inspectors noticed something that should not have been there. Small holes in the carburetor casting. Not factory holes, not standard passages, precisely machined openings that had no legitimate purpose. At the same time, the inspector noticed Schrader's crew members shifting uncomfortably, looking at each other. The kind of body language that experienced inspectors learn to read. The silent communication that says, please do not look any closer at that particular area. So, the inspector looked closer. He picked up a piece of safety wire, standard tool in any racing garage, and threaded it through one of the holes in the carburetor body. The wire went in. It traveled through the casting, and it came out through the intake manifold on the other side of the restrictor plate. The pathway was unmistakable. Air could flow from above the plate to below the plate through a route that completely bypassed the restriction. Gary Nelson was called over. He threaded the safety wire through the passage himself. He later described the moment to reporters with what sounded like genuine admiration mixed with professional obligation. He said that once he saw the wire come through, he knew exactly what he was looking at. He thought, and these are close to his exact words, "These guys are pretty smart." In all his years as a crew chief, he said, he had stared for hours at carburetors and restrictor plates trying to figure out how to get more air to the engine. He never saw this approach. Nobody had presented it to him. Nobody had even hinted at it. It was original work. Nelson examined the full assembly methodically. The carburetor had drilled passages. The intake manifold had matching passages. The connection point between the two, the bridge that would complete the circuit, was designed to be the stud, the bolt that was supposed to be hollow through its core. 3 separate components, all machined to function as a single integrated bypass system, a miniature wind tunnel hidden inside parts that every inspector had looked at thousands of times without ever questioning their internal geometry. Here's where it gets really interesting though.
Nelson's team noted something critical during their examination. The hollow stud itself, the connecting piece that would have made the entire system functional, was not installed. The passages in the carburetor were there. The passages in the manifold were there. But the bridge between them, the hollow bolt, was missing. Without it, the drilled passages were dead ends, blind holes leading nowhere. Air could not actually flow through the system as configured on the car that day. This detail would become the centerpiece of the most creative defense in NASCAR inspection history. But before the defense came the penalty. NASCAR moved fast. Schrader and car owner Rick Hendrick were immediately hit with a 4-race suspension. At the time, this was the most severe penalty handed down in Winston Cup racing in over 2 years. The message was supposed to be clear and unambiguous. You do not mess with the restrictor plate. The response from Hendrick Motorsports was swift, public, and carefully orchestrated. Jimmy Johnson, the team's general manager, not the driver who would later race for the organization, held a press conference at Daytona the following day. He laid out a narrative that was either a perfectly reasonable explanation or a masterpiece of damage control, depending on your level of cynicism. The restrictor plate engines, Johnson explained, were built and supplied by B&R Engineering, a vendor operation in Winston-Salem, North Carolina, that was partially owned by the Hendrick family. An engine builder at B&R named Kenny Bingham had experimented with this bypass system approximately 2 years earlier as part of a testing and development program. The drilled passages were remnants of that experiment, artifacts, leftovers. Bingham was supposed to have filled the holes and restored the components to legal specification before the engines shipped to the race team. He never got around to it. The parts ended up on Schrader's car by oversight, not by design. It was an accident, Johnson insisted. A quality control failure, not an intentional attempt to circumvent the restrictor plate. And then Johnson made the argument that would prove most effective with the appeals panel. He pointed out the missing stud. The system was incomplete. Without the hollow bolt connecting the carburetor passages to the manifold passages, the bypass could not function. No air could flow. No additional horsepower could be generated. The drilled passages were, in their current state, nothing more than evidence of a past experiment that should have been cleaned up but was not. If Hendrick Motorsports had been actively cheating, Johnson argued, why would they have put this engine on the number 25 car? Ken Schrader qualified 15th. If you had a secret weapon that could give you a meaningful horsepower advantage at Daytona, would you not install it on Jeff Gordon's number 24 car? Or on Ricky Rudd's number 5? Why waste the competitive advantage on a car that was running mid-pack in qualifying? It was a reasonable question. It was not an airtight defense, but it had logical weight. Here is the thing about that defense. It might have actually been true. At least partially. The system as found on Schrader's car genuinely would not have worked without the hollow bolt connecting the passages. Whether the omission was an honest mistake by a forgetful engine builder or a calculated decision to have plausible deniability of caught is a question that only the people inside B&R Engineering could answer definitively. And they were not offering additional details beyond what Johnson had presented publicly. Schrader's appeal went before a 3-member panel of the National Stock Car Racing Commission on July 6th, 5 days after the discovery. Engine builder Kenny Bingham testified alongside Rick Hendrick. The hearing lasted 3 hours. Arguments were made, evidence was reviewed, technical testimony was given about the functionality, or lack thereof, of the incomplete bypass system. When the panel emerged with their decision, they reversed the suspension entirely. No races missed. They reduced the penalty to a fine of $5,000 each for Schrader and Hendrick, $10,000 total. To put that in perspective, Ken Schrader had earned $37,000 for his third-place finish in the Pepsi 400 that same weekend. The fine was less than a set of tires for a race weekend. It was the cost of doing business at its most trivial. NASCAR was furious, though they expressed it in carefully measured public language. Chip Williams, the sanctioning body spokesperson, called the Appeals Commission's decision pretty disappointing. He said NASCAR believed suspension was the only proper course of action and that the organization was going to have to sit down and regroup. Reading between those diplomatic lines, NASCAR felt their own appeals process had undermined their authority. They had caught what they believed was a clear attempt to beat the restrictor plates, handed down a serious penalty, and watched it evaporate into a nuisance fine. The message sent to every crew chief and engine builder in the Winston Cup garage was confusing at best and permissive at worst. You can drill secret passages in your carburetor to bypass a safety-mandated device, get caught, and walk away with the equivalent of a traffic ticket.
But that confusion, that gray area between what happened and what could be proven, was itself a feature of the competitive landscape. The line between innovation and cheating in NASCAR has never been drawn with permanent ink. It shifts, it blurs, it depends on who is doing the drawing and who is doing the crossing. Darrell Waltrip, who knows something about both sides of this equation, summed it up after he got caught using nitrous oxide at the 1976 World 600 at Charlotte. He said, "If you don't cheat, you look like an idiot. If you do cheat and don't get caught, you look like a hero. If you do cheat and get caught, you look like a dope." Put that on a plaque and hang it in every race shop in North Carolina. Now, let me walk you through the physics of why the restrictor plate created such an extraordinary engineering challenge and why teams were willing to risk everything to defeat it. The plate works on a principle called choked flow. When air passes through a constriction, it accelerates. This is basic fluid dynamics, the same reason water speeds up when you put your thumb over the end of a garden hose. As the pressure differential across the restrictor plate increases, which happens when the driver goes to wide open throttle and the engine is demanding maximum air, the velocity of the air flowing through those four holes increases proportionally. At a certain critical pressure ratio, the airflow velocity through the holes reaches the local speed of sound. When this happens, the flow is said to be choked. And here is the key. Once the flow is choked, it does not matter how much harder the engine tries to pull air through those holes. The velocity cannot exceed the speed of sound through that restriction. You have hit an absolute physical ceiling. The speed of sound is the speed limit, and no amount of engine vacuum or cam timing or header tuning can push past it. This is why the restrictor plate is such an effective power limiter, and it is also why even microscopically small changes to the plate or the area around it matter enormously. Consider the mathematics for a moment. The flow through a choked restriction is directly proportional to the total cross-sectional area of the openings. If each of the four holes has a diameter of 1 inch, the total flow area is approximately 3.14 square inches. Now add 1/1000th of an inch to the radius of each hole. 1/1000th. You cannot see that difference with the naked eye. You would need precision measuring instruments to detect it. But that tiny increase raises the total flow area by roughly 0.0125 square inches. At choked flow conditions with the pressure ratios present in a racing engine, that translates to approximately 2 to 3 additional cubic feet of air per minute reaching the combustion chambers, which translates to measurable additional horsepower. Now multiply that across 4 holes, or combine it with a smoother bore finish inside the holes that reduces turbulent boundary layer effects, or use a gasket that is 0.003 of an inch thinner than stock, reducing the effective length of the restriction and improving the discharge coefficient. Each of these modifications is individually almost undetectable, but they stack, they compound, and in the compressed performance window of restrictor plate racing, where every car is operating at essentially the same power ceiling, these accumulated micro advantages become the difference between leading the draft and watching it drive away from you. The hollow bolt approach attacked the problem from a completely different angle. Instead of trying to squeeze marginally more air through the plate, it created a path around it entirely. Even a modest hollow stud, say a 1/4 inch internal bore, operating under the manifold vacuum conditions present at wide open throttle, could theoretically add a meaningful volume of additional airflow. Depending on the passage dimensions, the surface finish inside the hollow core, and the pressure differential, engineers estimated such a system could be worth somewhere between 15 and 25 additional horsepower. At a superspeedway where the entire field is running at 190 miles per hour in a tight draft, that is not a subtle advantage. That is the difference between choosing when to make your move and having the move made for you. But the significance of the hollow bolt discovery extends far beyond one car at one qualifying session. It was simply the most elegant expression of an engineering philosophy that pervaded the entire restrictor plate era. Throughout the late 1980s and the 1990s and into the 2000s, teams explored every conceivable method to move unauthorized air past that aluminum barrier.
The catalog of approaches reads like a graduate-level textbook on creative fluid dynamics and material science. Some teams had intake manifold castings produced with microscopic porosity in the walls. The metal looked solid, it measured solid, but at the molecular level there were tiny interconnected voids in the casting that allowed air to seep through the manifold walls themselves, bypassing the plate through the structure of the metal rather than through any discrete passage. NASCAR eventually caught on to this by pumping colored dye through the intake system under pressure and checking for any traces of the dye weeping through the exterior surfaces of the manifold. If color showed up on the outside, the manifold was porous, and the team had a problem. Other teams angle milled the mating surfaces of the carburetor and manifold. By machining these surfaces at a slight deviation from perfectly flat, they could create hairline gaps around the perimeter of the restrictor plate. The plate would sit in its designated location, look properly sealed to visual inspection, but air would leak around its edges through gaps thinner than a human hair. Individually insufficient to make a noticeable difference, collectively around the full circumference of the plate, potentially worth several horsepower. Then there were the gasket tricks. Some teams used gaskets between the plate and the manifold that were slightly undersized or had bolt holes that were offset by a few thousandths of an inch from the standard position. When compressed during assembly, these gaskets created thin crescents of open space around each restrictor hole, effectively enlarging the flow area without modifying the plate itself. The plate was legal. The gasket just happened to not quite cover all of it. Teams also discovered that the edges of the restrictor plate holes themselves offered an opportunity. A stock restrictor plate has holes punched or drilled with sharp, square edges. From a fluid dynamics perspective, a sharp edge orifice is actually less efficient than one with a radiused entry. The sharp edge creates flow separation and turbulence right at the entrance to the hole, which reduces the effective flow area below the geometric area. A ball-peen hammer, some patience, and a practiced hand could subtly reshape those sharp edges into a gentle radius, creating a smoother entry for the airflow. You are not making the holes bigger, you are making them more efficient. The plate would still measure at the legal diameter through its center, but the improved edge geometry could be worth 5 to 10 horsepower by reducing the parasitic losses at the restriction point. Teams did this routinely for the Twin 125 qualifying races and hoped nobody measured the edge profile too carefully afterward. And then there were the approaches that went beyond subtle modification into outright mechanical deception. Charlie Glotzback, back in 1970 at Daytona, had a system that makes the hollow bolt look conservative. His crew installed a sliding panel mechanism on the carburetor connected by a piano wire that ran through the firewall into the cockpit. During inspection, the panel was closed. The plate was fully effective. Everything looked legal. But once the race started, the driver could pull the wire. The panel slid open. Air bypassed the plate entirely. The engine went from restricted to unrestricted power at the pull of a cable. The driver controlled the cheat from behind the steering wheel, activating it on the straightaways for maximum speed and presumably deactivating it if he thought anyone was watching too closely. In 1970, NASCAR's inspection capabilities were limited. The sport was still regional in many ways, and the penalty for getting caught was essentially a stern conversation. Different era, different stakes. Perhaps the most audacious restrictor plate defeat of all time did not even happen in NASCAR. It happened in the World Rally Championship in 1995. Toyota Team Europe was running the Celica GT4 with mandatory restrictor plates limiting airflow to the turbocharger. Their engineers designed a system using hidden Belleville spring washers in the restrictor plate mounting hardware. Belleville washers are conical disc springs, and they have a specific mechanical property that made them perfect for this application. At rest, or during inspection, the spring washers held the restrictor plate firmly in its legal position, seated perfectly against the turbo inlet. But under boost, at full throttle during competition, the pressure in the intake system compressed the Belleville washers. This allowed the plate to shift approximately 5 millimeters away from the turbo inlet. That gap, small as it was, allowed unmetered air to flow around the edges of the plate and into the turbocharger. The result was approximately 50 additional horsepower over the regulated limit of about 300. On gravel stages where traction was limited, that extra power was devastating. The genius of the system was that the moment the engine returned to idle, the moment a scrutineer released the hose clamps during a technical inspection, the Belleville washers sprang back to their relaxed position and pushed the plate firmly back into its legal seat. The cheat was self-concealing. It only existed under the exact conditions where it was needed and automatically disappeared when it was not. It took the FIA, the governing body of world motorsport, nearly an entire season to figure out what Toyota was doing. When they finally did, the penalty was catastrophic. Toyota was banned from the World Rally Championship for 2 years. Careers were ended. Reputations were destroyed. The Toyota WRC cheating scandal remains one of the most infamous episodes in the history of international motorsport. But here is what most people do not realize about the connection between that Toyota scandal and what was happening simultaneously in NASCAR. The underlying engineering philosophy was identical. Find a way to make the restriction variable, legal when someone is looking, illegal when the car is at speed. The technology differed because the applications differed. Turbocharger versus carburetor, rally car versus stock car. But the thinking was the same, and the thinking was brilliant. The consequences of restrictor plate cheating in NASCAR extended far beyond individual penalties and fines. Every bypass that was discovered, every trick that was uncovered, led directly to new inspection protocols. The hollow bolt discovery led to more thorough fastener checks. Inspectors began cataloging bolt types and cross-referencing them against known standard components. Porous manifolds led to dye penetrant testing becoming a routine part of superspeedway inspections. Tricky gaskets led to NASCAR eventually supplying standardized gaskets that teams were required to use without modification. Modified plate edges led to post-race measurement of restrictor plate hole geometry using precision instruments that could detect changes measured in 10,000ths of an inch. By the early 2000s, the technical inspection process at Daytona and Talladega had become almost forensic in its thoroughness. Multiple inspectors, specialized measuring equipment, documented procedures, chain of custody for critical components. It resembled a crime lab more than a racetrack garage. And teams still found edges. They always do. In 2001, at the Daytona 500, NASCAR penalized 18 teams for various technical infractions. 18 out of 43 starters. Nearly half the field was found to be in violation of one rule or another. The infractions included illegal fuel additives designed to increase the energy content of the gasoline beyond the spec fuel's rating, unapproved air deflectors that altered the aerodynamic profile of the cars, and modified fuel cells that allowed teams to carry more fuel than the regulated maximum. That race, the race where Dale Earnhardt lost his life on the final lap, was also a cavalcade of technical violations. Everyone was pushing. Everyone was searching for the edge. And the man who pushed hardest at superspeedways, who searched most relentlessly for every possible advantage, was Earnhardt himself. The Intimidator hated restrictor plate racing with a genuine, publicly stated, frequently repeated passion. He despised what the plates did to the competition. He hated how the restricted horsepower bunched the entire field into tight packs, where one mistake by any driver, even a driver 20 positions behind you, could trigger what became known as the big one, a chain reaction crash that could collect half the field in a single incident. He said this publicly, repeatedly, to anyone with a microphone or a notebook. After winning at Talladega in the fall of 2000, his 76th and final career victory, Earnhardt told reporters flatly that he hated restrictor plate races. All of them. He did not distinguish between Daytona and Talladega. None of them were good, he said. He had been saying variations of this for over a decade. After NASCAR tightened restrictions on springs and shocks at superspeedways before the 2000 season, further reducing the team's ability to tune their cars for individual advantage, Earnhardt complained publicly that the rules had taken racing out of the hands of the drivers and crews. He called the racing at Daytona a joke. And then, in one of those contradictions that made Earnhardt so compelling, he went to Talladega and passed 17 cars in the final 4 laps to win from 18th place with 5 laps remaining, in a racing format he said was ruined, using skills that the format supposedly made irrelevant. The irony was deep enough to drown in. Despite his contempt for the format, nobody in the history of the sport mastered restrictor plate racing like Dale Earnhardt. 10 wins at Talladega alone, the most by any driver in history. 3 points-paying victories at Daytona, plus 6 Busch Clash wins and 12 twin 125 qualifying race victories. Across all restrictor plate events throughout his career, his record is not just the best. It is not even close to being challenged. Statistical analysis of superspeedway performance among all drivers with significant career starts at Daytona and Talladega shows Earnhardt's numbers in a category entirely by themselves. No other driver's results are in the same vicinity. He understood something about pack racing that most other drivers were still trying to figure out: the aerodynamics of drafting, the way air moved between cars running nose to tail at 190 miles per hour, when to push the car ahead of you, when to pull back and let the draft pull you forward, when to duck low and slingshot past on the inside, when to go high and use the clean air at the top of the track. His crew chief, Andy Petrie, once said that Earnhardt could see the air, not feel it, see it. As if the invisible fluid dynamics happening around 43 cars at nearly 200 miles per hour were visible to him in a way they were not visible to anyone else. The engine in his car might have been choked down to 450 horsepower, same as every other car on the track. But in Earnhardt's hands, the laws of aerodynamics became a weapon that no restrictor plate could neutralize. And then there is the open question that hangs over Earnhardt's legacy like a ghost you cannot quite see. The Intimidator himself used nitrous oxide to qualify for his very first NASCAR race, 1975, Charlotte Motor Speedway, the World 600. His car was underfunded, fielded by a small operation called Negra Racing with barely enough money to make the trip. The car was slow, too slow to qualify on its own merits against the established teams, so someone made a decision. Tommy Russell, who was there that day, recalled years later that a nitrous oxide bottle was hidden under the driver's seat. Earnhardt was literally sitting on it. The nitrous provided a burst of additional oxygen to the combustion process, temporarily boosting horsepower well beyond what the engine could produce on gasoline and atmospheric air alone. They qualified. They made the race. They ran it without the nitrous and finished 22nd. Dale Earnhardt's entire career, every championship, every Daytona 500, every iconic moment, began with a cheat. His son Dale Jr. found out about the nitrous bottle decades later and was genuinely stunned. The greatest stock car driver of his generation started his first race by breaking the rules before the green flag ever dropped. Richard Childress Racing, which fielded Earnhardt's famous Black No. 3 from 1984 until his death in 2001, was never directly caught in a major restrictor plate scandal. But there is an old saying in the NASCAR garage that gets attributed to almost everyone who has ever turned a wrench on a race car: if you ain't cheating, you ain't trying. The crews at RCR were nothing if not relentlessly competitive. Whatever edges they found at superspeedways, if they found them, stayed hidden. The best cheats, by definition, are the ones nobody ever discovers. Now, today, the restrictor plate itself is gone. After the 2019 Daytona 500, the last Cup Series race run with the traditional flat aluminum plate, NASCAR transitioned to tapered spacers. These are more sophisticated airflow restriction devices that use gradually tapering internal passages instead of the sharp-edged flat holes of the old plate. The geometry is more complex. The spacers are supplied as sealed, standardized units manufactured to tight tolerances, and the tapered design actually improves fuel atomization and throttle response compared to the abrupt restriction of the flat plate, while still limiting power output to approximately 510 horsepower at superspeedways. The tapered spacer is harder to cheat. There is no flat surface to bypass, no simple gasket line to exploit, no bolt holes that conveniently pass through the restriction zone in a way that could be co-opted for unauthorized airflow. The engineering challenge of defeating it is an order of magnitude more complex than beating the old plate. But the principle remains identical: limit the air, limit the power, keep the cars below 200 miles per hour, keep the fans safe in the grandstands, and hope the engineers do not find a way around it. They will, of course, they always do. Greg Zipadelli, who served as crew chief at Stewart-Haas Racing and Joe Gibbs Racing, once said flatly that no NASCAR race car is 100% legal. Every car on the grid has something, some edge, some interpretation of the rules that bends without quite breaking. It is just a matter of whether NASCAR finds it and whether they consider it a violation or an innovation. That distinction, the space between clever engineering and cheating, has never been clearly defined, and that ambiguity is not a bug in the system. It is the system. It is what drives the innovation. It is what makes the engineering compelling. It is what keeps the smartest mechanical minds in motorsport lying awake at 3 in the morning staring at a component that everyone else considers completely understood, wondering if there is something hidden inside it that nobody has thought of yet. That ethos has not changed since Smokey Yunick was stuffing basketballs into fuel tanks to displace gasoline above the legal limit, and Junior Johnson was filling frame rails with lead shot to manipulate the weight distribution of his cars. The technology got more sophisticated, the inspections became more rigorous, the fines got larger, the suspensions got longer, but the fundamental dynamic, intelligent and creative people trying to find the advantage that the rules were specifically designed to prevent, is as old as organized racing itself. It predates NASCAR. It predates the automobile. It is human nature compressed into a competitive framework where thousandths of an inch and fractions of a horsepower separate winners from everyone else. Go back to that hollow bolt. Think about it for a moment. Someone sat in a machine shop, probably in Winston-Salem, probably late at night when the regular work was done and the creative work could begin. They looked at a standard intake manifold stud, a piece of threaded steel so ordinary, so unremarkable, so invisible in its ubiquity that no inspector in the history of the sport had ever questioned one. It holds things together. That is its entire purpose. That is all anyone has ever asked of it. And this person looked at that stud and did not see a fastener. They saw a pipe. They saw a hidden channel for airflow that was not supposed to exist. They saw 15 or 20 or 25 extra horsepower concealed inside a component that every mechanic in every race shop in the country would walk past 1,000 times without a second thought. That is not cheating in the way most people understand cheating. That is engineering operating in the space between what the rules explicitly state and what the rules were intended to prevent. It is the gap between the letter and the spirit. And exploiting that gap is the same creative impulse that has produced every great race car ever built. Find the advantage nobody else can see. Exploit the gap between intention and enforcement. Do it so cleanly, so invisibly, so elegantly, that even the inspector, the man who himself was a former crew chief, who spent his own career trying to solve these same puzzles, has to pause and admire the work before he reaches for the penalty sheet. That kind of thinking built NASCAR. The restrictor plate was designed to stop it, and that kind of thinking guaranteed it never could.